Yeah, welcome. So in the last lecture we have discussed about the introduction to graphs. So in this lecture we will be discussing about graph representations. That is, if we want to use graphs in data structure, how should we represent? That is what we are going to discuss. But before that, I want to clarify certain things from the last lecture regarding this connected component. Okay, so there is a change in that explanation. The connected component of an undirected graph is a maximal connected subgraph. That is, actually these two are one graph, right? But it's a disconnected graph. This graph it's called as G4. This graph G4 is not connected. Now this graph is having two subgraphs. This is subgraph 1, which is called as H1. Subgraph 2 is called as H2. Okay. These two subgraphs by themselves they are connected. The subgraph H1 is connected and the subgraph H2 is connected. So this graph is having two connected component. Okay, and this graph does not have any other further connected component. So that is called as maximal connected subgraph. Okay, here this particular graph contains two connected subgraph. So two is the maximal here, right? So that is called as maximal connected subgraph. Similarly, coming to strongly connected in the sense a directed graph or a digraph, directed graph is also called as digraph, is strongly connected if there is a directed path from VI to VJ and from VJ to VI. Okay, a strongly connected component is a maximal subgraph that is strongly connected. A strongly connected component is a maximal subgraph that is strongly connected. Again, this is similar with respect to what do you call directed graph. If you take this directed graph, this is not strongly connected. Why it is not strongly connected? Because the definition of strongly connected says that every vertex Vi should be connected to Vj and Vj also should be connected to Vi. Then only we can call it as strongly connected. So here if you see, 1 is connected to 2, but 2 is not connected to 1. 0 is connected to 1 and also 1 is connected to 0. This is both way. But here this connection is this way, connection is missing. Similarly, there is no direct connection from 0 to 2. This is also missing. If all these things are there, then it will be called as strongly connected graph. But this is not strongly connected. Okay. But if you take this graph, again this is one graph, we can call it as G4 or G5, whatever it may be. It's not two different graphs, it's a single graph. Okay. But if you see this graph has two subgraphs. This is subgraph 1, this is subgraph 2. Subgraph 1 is strongly connected because it has only two nodes and there is a connection from 0 to 1 and also there is a connection from 1 to 0. Subgraph 2 is also strongly connected because there is only one node, there is no other node to have a connection, so it is also strongly connected. So this graph, okay, this graph G5, it contains two strongly connected components. So these two are the maximum strongly connected component this particular graph contains, which is called as maximal strongly connected subgraph, okay, of this graph G5. Okay, so this is what about maximal connected graph and maximal strongly connected subgraph, right? Fine. Okay. So now let us move on to the today's topic, which is graph representations. See, there are different ways of representing graphs, but we are not going to discuss all those details. We are going to discuss only three types of representation. One is called as adjacency matrix representation. That is, we are going to represent a graph using a matrix, and this matrix is called as adjacency matrix. Right? The second method is by using a list. It is something similar to a linked list. Using a linked list style of representation, we are going to follow to represent graph. So this type of representation is called as adjacency list. Okay. And the third way of representation is called as adjacency multi-list. Right. So these are the three different ways of representation which we are going to discuss: adjacency matrix, adjacency list, and adjacency multi-list. Okay. In adjacency list, we will be discussing some one or two subcategories also. Okay. In adjacency matrix, there is only one style of representation. In adjacency multi-list also there is only one style of representation. But for representing using adjacency list, we have two styles. One is by using linked list, the other method is by using arrays. Okay. The adjacency list representation can happen in two ways, either by using linked list or by using arrays. So that both techniques we will be discussing, right? So this is the objective of this lecture. Okay, we are going to discuss how graphs can be represented in these three styles: adjacency matrix, adjacency list, and adjacency multi-list. Okay, fine. Without wasting time, we'll jump. So first we'll discuss about adjacency matrix. So before discussing all these things, let me show you an example so that things will be clear. See, let us assume these three graphs. This is graph 1, this is graph 2, okay. This is graph 3. These two are combinedly one graph. Okay. It's not two different graphs. So let us see how this graph should be represented using adjacency matrix. Now this graph can be represented using adjacency matrix in this way. So how it is represented in the sense here all these row represents different vertices. See this particular zeroth row, it represents vertex 0. This row represents vertex 1. This row represents vertex 2. This row represents vertex 3. Similarly, this column, the zeroth column represents vertex 0 of this graph. Everything I am telling is with respect to this graph. Okay. This column represents vertex 1. Okay. This column represents vertex 2. This column represents vertex 3. Now, how these values came in the sense, you just take vertex 0. So, this is 0, right? This is vertex 0. Okay, is it connected with vertex 0? There is no self loop, right? There is no self loop. Already we have discussed that we are not going to discuss any graph with self loop or with multiple links between two nodes, right? So there is no self loop, so there is no connection between from 0 to 0. Okay, so it is 0. There is no link from 0 to 0, right? From 0 to 1, from node 0 to node 1, so you have to, each row you have to map with each column. Okay, from node 0 to node 1, is there a link? Yes, so put a 1. Okay, from node 0 to node 2, is there is a link? Yes, so put a 1. From node 0 to node 3, is there is a link? Yes, so put a 1. Node 1 to, now second row, come to the second row. Node 1 to node 0, is there is a link? Yes, put a 1. Node 1 to node 1, is there a self loop? No, 0. Okay. Node 1 to node 2, is there is a link? Yes. So keep a 1 here. Node 1 to node 3, is there is a link? Yes. So keep a 1 here. Right? Similarly, so on and so forth, continue. Node 2 to node 0, yes, 1. Node 2 to node 1, yes, there is a link 1. Node 2 to node 2, no, there is no self loop, 0. Node 2 to node 3, yes, 1. Again, node 3 to 0, yes. Node 3 to 1, yes, 1. Node 3 to 2, yes, 1. Node 3 to 0, no. Okay. So this is what type of graph? This is an undirected graph. Okay. So in an undirected graph, you can always see that the diagonals will be 0. This is a diagonal, right? So this diagonal entry will be always 0 in an undirected graph, because not only in an undirected graph, in a directed graph also the diagonal entry will be 0. Whether it is undirectional, whether it is undirected graph or a directed graph, the diagonal entries will be 0, because we are not going to discuss any graph with self loop. Okay, because these diagonal entries represent all the self loop. This is 0 to 0. This first diagonal entry 0 to 0. This is 1 to 1. This is 2 to 2. This is 3 to 3. Okay, right. And in an undirected graph, and undirected, when an undirected graph is represented as an adjacency matrix, that adjacency matrix will be symmetric. When an undirected graph is represented as an adjacency matrix, that adjacency matrix will be symmetric. Symmetric means if you take any row, that row values will be equal to that particular column. This is 0th row. What are the values in 0th row? 0, 1, 1. If you take the 0th column, it will also have the same value, 0, 1, 1. Okay, so like that you can take any row, right? If you take if you take if you take the first row, if you take the first row, it contains 1 0 1 1. Okay, if you take the first column, I mean numbering starts from 0, right? So this is 0th column, this is first column. It is also 1 0 triple 1. Okay, you can map with any row and any column, it will be similar. So when you represent an undirected graph using an adjacency matrix, that adjacency matrix will be symmetric. Okay. Now let us say graph 2. Graph 2, this is a directed graph. This is a directed graph, it contains only 3 nodes. So the matrix will be having only 3 rows and 3 columns. So 3 rows 0, 1 and 2. 0 is one node, 1 is another node, 2 is another node. Okay. This is 0, 1 and 2 for the column. Okay. So diagonals you can directly fill up zeros because there is no, we are not going to have any self loop. So let us assume we have filled this. Then 0 to 1, this is a directed graph. Okay. So 0 to 1, node 0 to node 1, is there is a path? Yes. So put a 1. Node 0 to 2, if there is a direct path, only direct path we are seeing. Okay. Node 0 to 2, if there is any direct connection? No. So put a 0. Okay. Then come for the next node, node 1. Node 1 to 0, is there is a link? Is there is an edge? Yes. Put 1. Okay. Node 1 to 1, no self edge, so 0. Node 1 to 2, is there is a link? Yes. Put a 1. Okay. Now come to the third, to the second node. Node 2 to 0, is there is a link? No link, no edge. Node 2 to 1, is there is edge? No. No, we have 1 to 2, but there is nothing from 2 to 1 because it's a directed graph, so put a 0. Node 2 to 2, no self loop, 0, right? Okay. So you can see this is an adjacency matrix for a directed graph. This adjacency matrix, it is not symmetric. You take the first row is 0 1 0 and the column is also 0 1 0. This is symmetric, this is a coincidence. But you take the second row. Second row is what? 1 0 1. Take the second column, it is 1 double 0. Okay, or you can call this as first row, this is first column. This is, if you call this as first row, 0th row, then this will be first column, then this will be 0th column and this will be first column. Okay, so this column, this row is 1 0 1, whereas this column is 1 0 0, so it's not symmetric. This row, okay, the last row is triple 0, whereas the last column is 0 1 0, so it's not symmetric, right? Okay, so this is how we create adjacency matrix, right? You take this graph, this is a disconnected graph. It's not connected. Okay, it's not because there is a, actually this two are single graph only, but there is some disconnection in between. Okay, so this graph, how do we represent? So it contains how many nodes? 8 nodes, 0 to 7. Okay, so this is node 0 or row 0, row 1, row 2. Each row represents one node. Row 3, row 4, row 5, row 6, row 7. Okay. Similarly, this is column. Column 0, column 1, column 2, column 3, column 4, column 5, column 6, and column 7. Okay. And column 7. Okay. Now you can see 0 to 0. From you see 0 to 0, diagonals anyway you can fill up with zeros because we are not going to have any self loop. Okay. 0 to 1 is there is a link. Yes. So 1 come here. 0 to 2, yes, so 1. 0 to 3, there is no direct connection, so 0. Okay. 0 to 4, these are two different subgraphs, they are disconnected, so it is 0. 0 to 5, 0. No, nothing in this other subgraph. Okay. 0 to 6, 0. 0 to 7, 0. Okay. So this subgraph contains 0, 1, 2 and 3. So up to this 0, 1, 2, 3, you can see this entire part is 0 because 4, 5, 6 is in the other subgraph, right? Okay. So like this, every row and every column can be filled up. Okay. Like this, every row and every column can be filled up, right? Okay. Fine. So so again you see this is a undirected graph. Okay, you can see this is symmetric. You can see this is symmetric. You see you take the any row. For example, let us take this row. Okay, this is row number what? 0 1 2 3 sorry 0 1 2 3 4 5. Okay, it's row number 4. It's what? 4 zeros 1 0 1 0. 4 0 1 0 1 0. It's row number 0 1 2 3 4 5. Okay, 0 1 2 3 4 5. The same column you take. It is what? 4 zeros 1 0 1 0. It's same. It's same. Okay. So the point is when you when you create an adjacency matrix from an undirected graph, that adjacency matrix will be symmetric. Okay, right? Okay, fine. So this is how adjacency matrix works, right? Okay. Now let us see certain important things from like what we can observe from this adjacency matrix. Okay. So from this adjacency matrix, we can calculate the vertex, sorry, degree of a vertex. We can calculate the degree of a vertex using this particular formula. Adjacency matrix of sigma j equal to j equal to 0 to n minus 1. N represents the number of nodes. Okay. If number of nodes is 8, then it will go from 0 to 7. If number of nodes is 5, it will go from 0 to 5. Adjacency matrix of I comma j. That is, I is not changing. I represents any row. Okay, and I represents any row. Row number also ranges from 0 to n minus 1. But here I is something, if I is 0, it represents 0th row. Okay, it represents 0th row or 0th node. If I is 4, it represents 4th row or 4th node. Okay, but j is going to change. So what we are doing, we are adding, that is in a particular row, we are adding all the elements of the respective columns. Okay, that will give you the degree of a vertex. Okay, that will give you the degree of the vertex. So how is that? You may ask, how is that? So let us take one example. Let us say, for example, this particular, you take this particular graph, take this particular node. What is its degree? It contains 3 edges, 1, 2, 3. So its degree is 3. Okay, so to now how can we find the degree from the adjacency matrix? That is the question. So go to row 0. Which node you want to find? 0th node. So go to node 0. Okay, and count all these things. In the 0th node, what are the values? You just count. 0 plus 1 plus 1 plus 1, that is 3, which is equal to 3. So that is nothing but the degree of that particular node. Okay, that is nothing but the degree of the node. Okay, right? So, but this is with respect to an undirected graph. Okay, this is with respect to an undirected graph. This logic will work only for undirected graph. Okay, you take, for example, you take node 3. You take node 3. Its degree is 1, 2, 3. Okay, so this is 0, 1, 2, 3. Here also you can come and add, right? Or let us take here node 5. Node 5's degree is what? 1 and 2. So go to 5th row. Count from 0. 0, 1, 2, 3, 4, 5. Okay, count 0, all zeros, only 2 ones are there, 1 and 1. So it is what? 2. So the degree of node 5 is 2. Okay, so this is how we find the what you call the degree of a particular node or a particular vertex from an from the adjacency matrix of an undirected graph. Okay. Now coming to the directed graph. So directed graph has two types of degrees. Okay, in degree and out degree. They have two types of degrees. One is called as in degree, the other one is called as out degree. Okay. Now how will you calculate the in degree? Now to calculate the in degree, right? Now to calculate the in degree, you have uh, to to calculate the in degree for a particular node. You have to sum up all the elements in different rows. Now the column will be constant. See, now the column will be constant. The row will change. The row will change. See here. See, only the difference is what here they have. It is called as adjacency matrix. Instead of here, you can also write here adjacency matrix. That is just a notation. Or here instead of adjacency matrix, we can mention as here. This is just a notation, nothing else. Okay. J equal to 0 to n minus 1. Here also j is equal to 0 to n minus 1. Here it is a of j comma I, whereas here it is a of I comma j. I is rho. Here rho is constant. When you want to calculate the degree of an vertex in an from the adjacency matrix of an undirected graph, rho is constant, column is changing. Okay, but when you want to calculate the n degree from the adjacency matrix of a directed graph, here what is happening? Rho is changing. See, first is always rho. Okay, rho is changing, column is constant. Column here is I is there. There is nothing like I. So I can take any value, but any value in the sense any value between 0 to n minus 1, because we have only that many nodes. Okay, so if I is 0, then we are talking about node 0. Okay, so it means column 0, but j is changing. J is going to change. Are you getting right? So for example, if you want to calculate the, so this is how we calculate the in degree. So for example, if you want to calculate the in degree, this is a directed graph, right? If you want to calculate the in degree of this node has how many in degrees? It has only one in degree, right? Which is coming towards, I mean, just coming towards it, right? The in degree represents what? The number of incoming edges. It has two outgoing edges and one incoming edge. Okay. So this is which node? This is which node? This is node 1. Node 1. Okay. So you go to the first column. This is 0th column. This is first column. Go to the first column. Here you add all the row values. Okay, because the formula what it says, this node, this should be constant. Here we are talking about we want to find the in degree of node 1. So the second thing represents always what? Column. Okay, so first column, we are going to first column, and then j is changing. So right, I is now column, j is the row. Okay, so add all these things. 1 plus 0 plus 1, 1 plus 0 plus 0, which is 1, right? Okay, so that is the in degree of node 1. Okay, if you want to calculate out degree, then it is the same formula which we are using to calculate the degree from an, what do you call, undirected graphs adjacency matrix. Okay, it is, or you can say it's just the reverse of this, a of I comma j. Now you keep I as constant. And the row will be constant. Add the for a particular row, add the different column values. Okay. So for example, if you want to calculate the out degree of node 1, how many out degrees it has? It has 2. So now go to row 1, row 0, this is row 1. In row 1, add all the column values. 1 plus 0 plus 1, that is 2. So its out degree is 2. Okay, right? So this is how we calculate the in degree and out degree of these nodes, right? Of these nodes. Okay, fine. Okay, so that's what this thing says. So here, whatever it says is whatever we have discussed here, how this matrix is getting filled, that's what being explained here. For a graph V equal to E, adjacency matrix of is represented as a two-dimensional matrix or an array. Okay, if there is an edge exists between two, if there is a direct edge exists between two vertex Vi and Vj, then in the respective entry of the adjacency matrix I comma j, there will be a 1. Otherwise, in the respected entry of the adjacency matrix, there will be 0. Okay. The adjacency matrix of an undirected graph is always symmetric. The adjacency matrix of a directed graph need not be symmetric. Okay. Need not be symmetric. It may be symmetric if there is an opposite edge for all the nodes. Okay. Right. For every vertex Vi and Vj, there is an edge from Vi to Vj and also from Vj to Vi, means then the directed graph also will be symmetric. Okay. Fine. So this is the representation in programming language. We will come to this later. Okay. So this is about adjacency matrix representation. Okay. So first thing we have done. Okay. There are different types of representation, right? The second, now we will move to the second type of representation, adjacency list. Okay. So you may ask why we should have different types of representation. So again, there are certain drawbacks or what do you call benefits with different techniques under different situations. Okay, so depending on the situation or depending on the need, any one of the representation will be chosen. Okay, so if you see the drawback with this adjacency matrix technique, what's the drawback in the sense? Say for example, if you want to find totally like uh, say say for example we want to find like how many edges are there. Okay, you want to answer the question like uh, how many edges are there in a graph. Okay, say let us say in a directed graph. Okay, say in a directed graph, how many edges are there that you want to find. Okay, so then what you have to do in a directed graph, you have to make n square search. You have to make n square search. Okay, okay, that is how this n square comes, you may ask. Okay, how this n square comes, you may ask. In both directed and undirected graph, you have to make n square search. Okay, but the number of edge, or you can say this is the formula to calculate the number of edge in a directed graph. Okay, from the adjacency matrix. Given the adjacency matrix, the graph is not given. Okay, you are not shown the graph. Given the adjacency matrix, how will you find the number of edges from a directed graph? Okay, so for that you have to perform n square searches. So this n represents the number of nodes or number of vectors. So this is a graph. This is the adjacency matrix of this particular graph. This particular graph contains how many vectors? Three vectors. So n is equal to 3. So it means that you have to perform 3 into 3 searches. It is 9 searches. Okay, 9 searches and sum up all that. That will be the result. Okay. So it basically it means that you have to search every location 0 and add 0 plus 1 1 plus 0 0 0 plus 1. I mean 0 plus 1 1 1 plus 0 1 1 plus 1 2 2 plus 0 0 sorry 2 plus 0 2 2 plus 1 3 3 plus 0 3 3 plus 0 3 3 plus 0 3. So the number of edges in this graph is 3. Are you getting? Right? But search, how many times you have to do? N square search. Okay. But if you want to find the number of edges in an undirected graph, then also you have to perform n square search and you have to add everything. But finally, to calculate the number of edges, the formula is n square by 2. The formula is n square by 2. Okay. That is, add up everything and divide that by 2. So, so again, you have to add 0 plus 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 1 4, 5, 6, 7, 8, 9, 10, 11, 12. So what you got? 12. Okay, 12 by 2. Divide that by 2. 12 by 2 is what? 6. So this particular graph contains 6 edges, right? So you can verify here. 1, 2, 3, 4, 5, 6. For example, this graph you want to do means you count all these things. 1 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 14. 14 by 2 is 7. Okay, 14 by 2 is 7. So you can check here how many edges it may be having 7 edges. 1, 2, 3, 4, 5, 6, 7, right? So this is how we find the number of edges from a graph. Okay, so basically, if you want to find the number of edges in any graph, whether it is an undirected graph or a directed graph, from an adjacency matrix, you have to perform n square searches. Without performing n square searches, you cannot find. Okay, right? So the time complexity is order of n square. So the time complexity is what? Order of n square. Okay. Of course, here you can ignore the diagonals. Here you can ignore the diagonals, but still the time complexity is going to remain the same. So actually, it is n square minus n searches, because diagonal will take n entries, right? So that diagonal you can remove, but still the time complexity is order of n square. It is not going to reduce. Okay. But by using the other technique, by using adjacency list, the time complexity can be reduced to this level. To what level? To order of n plus e level. Okay, to order of n plus e or e plus n. Okay, where n is the number of nodes and e is the number of edges. Okay, by using adjacency list technique, the time complexity to what do you call, to find the number of edges from a graph can be reduced from order of n square to order of n plus e. So that is the reason why we are moving from this technique to that technique. Okay, but it all depends on the situation, what way of representation you have to use. Okay, fine. So as we have said already, there are two ways of doing this. Okay, either you can have this adjacency list representation can be done either by using linked list or by using arrays. So first let us see the linked list way of representing. Okay. So this is a graph. For example, this graph you want to represent using adjacency list means first you have to create an array. Okay, array of pointers first we will create. This array of pointer contains how many locations means you will have that many locations which is equal to the number of nodes. So this particular graph contains how many nodes? 4 nodes, 0, 1, 2, 3. So you will create an array of pointer with 4 locations. You will create an array of pointer with 4 locations. Okay, that is each of these location is a pointer. You will create an array of pointers with 4 locations, that is each of these location is a pointer. Okay, now the 0th location of the array represents node 0. First location of the array represents node 1. Second location of the array represents node 2. Third location of the array represents node 3. Okay. Now from node 0 you see how many links are there and where are they. From node 0 to node 1 there is a link. Node 0 to node 2 there is a link. Node 0 to node 3 there is a link. Okay. So here we say 0 to 1. Okay, there is one here we create one linked list. So the linked list contains, we create one node in the linked list which contains the data part and a pointer. Okay, so 0, this is a point, this is just a pointer. Okay, it's array of pointers. So this points to this node 1, right? Node 1. Okay, and node 1 is pointing to 2. See, this is for our representation. We are saying node 1 is pointing to 2, but actually the meaning is what? 0 to 1 and 0 to 2. This is what you have to take. Our understanding is what? 0 to 1 we have a pointer. Everything is connected with this node 0 only. 0 to 2 we have a pointer. Okay, are you getting? Because here we have only one pointer, so that 1 is connected with 2. 1 is pointing to 2 and 2 is pointing to 3. But in reality it is what? 0 is pointing to 3. Okay, it's undirected graph, there is no arrow. This is just for understanding I am saying. Okay, fine. And it has only 3 edges. Okay, from 0 how many edges are there? Only 3 edges are there. 0 to 1 and 2 and 3. Okay, right? So there is nothing to do with this is only for way of representing. It is 1 to 2 and 2 to 3. But actually the meaning is what? 0 to 1, 0 to 2, 0 to 3. Right? Okay. Similarly for 1, if you see from 1 there are how many pointers? 3 pointers. 3 edges. 1 to 0, 1 to 2 and 1 to 3. Okay, so 1 to 0, actually there is another edge from 1 to 2. So for representing that, we are connecting this pointer of 0 is pointing to 2. Similarly, there is edge from 1 to 3. So that is represented through the pointer of 2 to 3. And 3's pointer is null. Okay, because from 1 we have only 3 pointers. Similarly for 2 and similarly for 3. Okay. So this way of representation is called as adjacency list. Now this is a list. Okay, this is not a matrix. So similarly, so either directed graph or undirected graph you can represent in this way. This is a directed graph. This is an undirected graph. Here how many nodes are there? 0, 1 and 2. Now you see. So you create first you create an array of pointers. And this array of pointers size will be what? 3. And what are they? 0, 1 and 2. From 0 to 1 there is a link. So 0 to 1. Is there any other link? Is there anything 0 to 2? No. So 0 to 1, after that it is null. 1, we have 1 to 0 and also 1 to 2. So 1 to 0 and then another pointer to 2. Okay. After that there is nothing. Because we have 1 to 0 and 1 to 2. Is 1 to 2 only we are representing through this pointer. Because we don't have extra pointers here. So we are utilizing the pointer of the before node. Right. From 2, is there any 2 from 2 is there any outgoing edge from 2? Basically this is only talking about outgoing edge with respect to a directed graph. Okay. In undirected graph it's either way, right? So with respect to a directed graph it's only talking about the outgoing edge. Okay. From 2 is there is any outgoing edge? No. So it is just null. Right? Okay. Similarly this is the adjacency list representation of this particular graph. Okay, if you see 0 to 1, there is a path from 0 to 1 and 0 to 2. So 0 to 1 and 0 to 2 is represented as 1 to 2. From 1, if you see, there is a path from 1 to 0 and 1 to 3. So 1 to 0 and 1 to 3 is represented as 0 to 3. From 2, if you see, there is a path from 2 to 0 and 2 to 3. So 2 to 0 and 2 to 3 is represented as 0 to 3. Okay. From 3 there is a path from 3 to 0, 3 to 0 and 3 to, sorry, 3 to 1 and 3 to 2. So 3 to 1 and 3 to 2 is represented as 1 to 2. Okay. So on and so forth, it is represented. Okay, fine. So this type of representation is called as list representation. Okay. In list representation, the order is not an important thing. So this is again, it is the same list representation of this particular graph which is given here. Okay. So it is not that you have to, this numbering should be in ascending order, like that. There is no compulsion. Okay. There is no, it is nothing like that, that this number should be in ascending order. No. So it is not that 0 to 1 and then 2, 3. No. Okay. It can be any order. That's what this is. That's what this is. Okay. Here also you have an array of pointer. Okay. This array will be in the proper order. 0th node, this represents 0th node, this first, second, third. But this need not be in a, it can be in any order. Okay. Because all these edges are equal. It is not that this is first link, this is second link, nothing. Anything you can take as first. Okay. So 0 to 3, again 0 to 3 is represented like this directly. 0 to 1 is represented using the pointer from 3 to 1. Okay. And 0 to 2 is represented using the pointer from 1 to 2. So the order can be anything. Here it is, see, 1 to 2, and then 1 to 0 is represented using the pointer from 2 to 0. And 1 to 3 is represented using the pointer from 0 to 3. So the order doesn't matter. That's what the point is. Okay, fine. Okay, so what are the observations we can have from this adjacency list in the sense? So these are the two observations. Sorry, okay. So there are some observations with respect to undirected graph, and there are some observations with respect to directed graph. Okay, so let us see. The observation with respect to undirected graph is the degree of a vertex in an undirected graph is just the number of nodes in the adjacency list. Okay, in the adjacency list, how many nodes are there? Here, nodes in the sense we are not talking about vertex. Here, nodes in the sense that in C we are creating node, no, linked list node. Okay, right? Linked list node. Here, nodes in the sense we are talking about linked list node. Okay, so this is vertex. This is one vertex. This is another vertex. This is another vertex. This is another vertex of the graph. 0th vertex, first vertex, second vertex. These are the nodes. This is one node. This is another node. This is another node. Okay. This is another node. This is another node. This is another node. Okay. Right. So what it says in the sense, the degree of a vertex in an undirected graph is the number of nodes in that adjacency list. For example, if you want to find the degree of node 2 from an adjacency list, you just count how many, degree of vertex. Let us use vertex for this vertex, and let us use node term for linked list node. Okay, if you want to find the degree of vertex 2 from the graph, right? Okay, you just count this number of nodes available in that particular vertex. How many nodes are there? 1, 2, and 3. So its degree is 3. You can come here and check. So 2 is having how many degree? 1, 2, and 3. Right? Let us take something else. Let us see what is the degree of 6. 6 degrees 2. Okay. So go to 6. This is 6. Count the, this is vertex 6. Count the number of nodes. Okay. 1 and 2. This is just a linked list, right? You know how to count a linked list. Even you can write a program for that. So 1 and 2. So that is the degree of vertex 6. Okay, so the degree of vertex 6 is 2. So this is how we find the degree of an vertex from an adjacency list. Okay, right. The number of edges in the graph, as we have already discussed, the number of edges in the graph, to find that in an adjacency matrix, it requires order of n squared time. Okay, but from an but if you want to find the number of edges from an adjacency list, we need only order of n plus e times. We need only order of n plus e times. You may ask, how is that? How is that in the sense that is better understood with the directed graph rather than with an undirected graph? Okay. So n represents, n is what? N is number of Here n represents number of vertex. Okay, n is number of vertex, n is number of vertex, and e is number of edge. Okay, e is number of edge. Okay, right. So you take this particular graph, this directed graph. How many vertex are there? 0, 1, 2, 3. So n is 3. How many edges are there? How many edges are there? 1, 2, 3. 3 edges are there. Okay. So our objective is to count what? The number of edges. Okay. And the number of edges, the complexity is n plus e. So n plus e is 3 plus 3, 6. 6 comparisons you have to make. That's what it says. At most you have to make how many comparisons? Six comparisons. Because here number of nodes is also 3, number of edges is also 3. So how you may ask, right? So how is that 6 comparison means? First you have to compare for every vertex. For all the vertex you have to compare. Okay. How many vertex we have? N vertex. Okay. In each of the vertex, how many times you have to compare? That depends on the number of nodes. Okay. So this vertex contains how many node? One node. So here you have to perform for vertex 0 you have to perform one comparison. This vertex contains how many nodes? 2. So here you have to perform two comparisons. This vertex contains how many nodes? 0. So here you have to perform 0 comparison. So but here also in this vertex also you have to come and check whether there is a link or not. So this is also counted. So so by default the number of node is counted. Even okay, by default even if you have a graph which is totally disconnected. Say I have a graph like this. 1, 2, 0. No edges at all. No edges at all. Okay. For in this graph also, if you want to find number of edges, at least you have to make 3 comparison. Okay, you will see what are the 3 comparison. You have to come and check the pointer of 0. Pointer of 0, you have to come and check pointer of 1 and pointer of 2. So I mean this array is an array of pointers, right? So array of the pointer of 0 is also null. Pointer of 1 is also null. Pointer of 2 is also null. So anyway you have to make 3 comparison. So this here 3 is nothing but n. N comparison is must. Okay, then for every node you have to make that many comparisons, that is equal to the number of nodes. Okay, in this case there are 3 nodes, so 3 comparison is must. And then number of nodes for the first node is, for the first vertex is 1, second vertex is 2, third vertex is 0. So 2 plus 1, 3. Are you getting? So 3 plus 3 is 6. Okay. Right. So this is the case for undirected graph. Sorry, directed graph. For an undirected graph also, whether it is a directed graph or undirected graph, to find the number of edges, you need only this much time, order of n plus e time only, not more than that. Okay. Because here how it is n plus e in the sense n part is same. You have to compare all the vertex, right? Okay. But here the thing is, say when you found an edge from 0 to 1, then you need not check for 1 to 0. This you need not count. Because already 1 to 0, 0 to 1 means 1 to 0 also you can take it for granted. It is because it is undirected graph. Okay. Similarly, when you found 0 to 2, you need not check for, when you found 0 to 2, you need not check for 2 to 0. So this will be striked off. Okay. When you checked for 0 to 3, you need not check for 3 to 0. Okay. Right. So how many comparisons so far we made? We made one for this vertex, that is 1, and this vertex contains 3 nodes. For each of the 3 nodes we have compared. So 3 plus 1, 4 comparisons already we made. This vertex, this graph contains how many vertex? What is n? N is 4, and how many edges? 6, I guess. 1, 2, 3, 4, 5, 6. So here we need maximum 10 comparisons. Okay. So 4 is done. Then 1 to 2. Okay, when you do 1 to 2, you need not do 2 to 1. So this will be cancelled. Okay. Right. So when you do 1 to 3, you need not do 3 to 1. So this will be cancelled. Okay. Fine. Now here how many comparisons we have made for this node? Anyway, for this vertex, we have to make one comparison, that is done. But here we have not made 3 comparisons. We have made only 2 comparisons. Because this 0 to 1 satisfies this 1 to 0. So here it is 2. Okay. So 3 plus 1 4, 4 plus 2 6, 6 plus 1 7, right? Okay. Now now we came to the next node. Anyway, you have to come here and check. Yes, so here 1 is counted now. This vertex you have to come. And then 2 to 3. When 2 to 3 is done, 3 to 2 is also done. So this will be strike off. Okay, right? So this is here how many comparisons we did? One comparison for this vertex and here for one. Okay, now how many totally? 3 plus 1 4, 4 plus 1 5, 5 plus 2 7. Okay, 7 plus 1 8, 8 plus 1 9. 9, right? Here anyway you have to come to 3 and check. But all these are already done. But still you have to count this, right? So you count everything. 4 here 4, 4 plus 3 7, 7 plus 2 9, 9 plus 1 10. So totally 10 comparisons. Okay. So the number of comparisons here is less to find the number of edges. There in an adjacency matrix is order of n square, but here it is order of n plus e. Here it is order of n plus e. Okay. Fine. Okay. Right. So an undirected graph with n vertices and e edges. Okay. An undirected graph with n vertices and e edges. Undirected graph. This is an undirected graph with n vertices and e edges will have n head nodes and 2e into e list nodes. Okay. That is n head means these are called as head nodes. You can call it as, we are in linked list, how we call it as head pointer. You can call it as head nodes. Okay. So n head nodes, and how many list nodes will be there? 2 into e. Okay. 2 into e. E is what? E is the number of edges. E is 6. So how many list nodes you have means 12 list nodes you have. In this case E is 6. So you have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is only for an undirected graph. Are you getting? Okay, fine. So these are the observations, right? And out degree of a vertex in a directed graph for any vertex. Okay, degree of a vertex in an undirected graph is you just count the number of nodes for that vertex. Okay. How to calculate the out degree of a vertex in a directed graph? Just count the number of nodes in the adjacency list. That's it. So this is an undirected graph. This is a directed graph. So now we are talking about directed graph. How to find the out degree? How to find the out degree of a directed graph from the adjacency list? Okay. So you have to just count the number of nodes in the particular vertex adjacency list. Okay. Say you want to find the degree out degree of node 1. What's the out degree of node 1? It has two what do you call? Two edges. Okay, one edge here and one edge in this direction. Okay, so its out degree is 2. Okay, so just to go here, which node? Node 1, and count the number of, vertex 1 and count the number of nodes 1, 2, so 2. Okay, if you want to count, identify the out degree of node 0, it has only 1, so it has only 1 node, so count that. If you want to find the out degree of node 2, it is what? It is, there is no out degree, so it is 0, it is null, so it is 0, right? Okay, fine. But how to find the integrity of a vertex in a directed graph? Actually, this is little complex. To find the integrity of a vertex in a directed graph, actually you have to traverse the entire data structure. Okay, if you want to find the integrity of a vertex from an adjacency list, you have to go through the entire data structure. Okay, so then only you can find the integrity. Okay, because what is integrity says. This says that 0 to 1. Okay, this says that there is something from 1 to 0. Okay, so if you want to find the integrity of 0, this is outgoing for 0. This is what 1 to 0 means. 1 to 0 means it is outgoing for 1 and incoming for 0. So you can count 1 here. But like that you have to, 1 to 2 is not counted. Like that you have to traverse entire tree. I mean the entire list. Sorry. Saying tree, the entire list, all the vertex of the adjacency list should be traversed. Okay, then only you can find the what you call integrity. So it is a little complicated. So there is another way to do that. What in the sense, it all depends on the application you are using. Okay, for example, in the program you are using, you want to often find the integrity, and then you have to work out means then we can represent then there is another way of representation which is called as inverse adjacency list. Right? If you want to, that is the program that you are using, in that you want to frequently find the a degree of a particular vertex, then instead of representing in a normal adjacency list fashion, we can represent in inverse adjacency list fashion. So what is that? It's just a reverse of this. See here, in adjacency list, what we are talking about, see, for example, you take this directed graph. Here 0 means we are taking only the out degrees. We are taking only the outgoing edges. From 0, what are the outgoing edges? 1, that only we are marking here. From 1, what are the outgoing edges? That is the outgoing edge from 0 and 2. That is only we are marking here. From 2, there is no outgoing edge. So this is the adjacency list. What is the inverse adjacency list for this? In the sense, you identify the incoming edge instead of outgoing edge. Okay. By default, adjacency list identify the outgoing edge, but instead now we will identify the incoming edge. Okay. Now we will identify the incoming edge. So what is that? So 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 how to do that in the sense? Sorry, something is happening. Yes. Okay. So how to do that in the sense? Uh, yeah, say I'll try to represent here. Say the initial part is same. We are going to create an array of pointers. This array of pointers will have that many number of vertex. So we have two vertex 0 1 and so the three vertex which is named as 0 1 and 2, right? 0 1 and 2. Now normally in an adjacency matrix we take the outgoing edges, but in the inverse adjacency matrix you have to take the incoming edges. 0 has how many incoming edges you see? This no vertex 0 has how many incoming edge? It has only one incoming edge. It has an incoming edge from where? From 1. So you say that 0 to 1. You say that there is a node from 0 to 1, which means that there is an incoming edge. There is an incoming edge to 0 from 1. That is the meaning. So getting the meaning is here now it's a not an adjacency matrix, it's an inverse adjacency matrix. So the meaning is there is an incoming edge from there is an incoming edge to 0 from 1. Okay. Okay. So there is an incoming edge to 0 from 1. That's the meaning, right? Okay. Now you take 1. 1 has how many incoming edge? Again 0 has only one incoming edge. 1 also has only one incoming edge. From where? From 0. Okay. So 1 to 0. Okay. What does it mean? There is an incoming edge to 1 from 0. Okay. There is only one incoming edge, so after 0 there is no pointer. So which means that there is an incoming edge to 1 from 0. Okay. Now take node vertex 2. Does it have an incoming edge? Yes. It has an incoming edge from 1. So it will be represented like what? Like this. 2 to 1. Which means what? There is an incoming edge to 2 from 1. Okay. There is an incoming edge to 2 from 1. Okay. Fine. So this is how we represent the what do you call inverse adjacency matrix. So you can see here for this graph 0 has one incoming edge from 1, 1 has one incoming edge from 0, 2 has one incoming edge from 1. Right? Okay. Right. So normally we represent the adjacency matrix in terms of outgoing edge. But if you want to frequently use the incoming edge, if you want to calculate the incoming edge from the adjacency matrix, then you can represent in this style, inverse adjacency style. Okay, right. So this is how we represent adjacency list using linked list. Okay. The another way of representation is using arrays. Okay. This can also be represented using arrays. So how to represent that in the sense? Say for example, this particular graph we want to represent in array. So this is a single graph, right? It's not a two different graphs. This is a single graph, but it is disconnected. Okay. So this graph contains how many vertex? It has basically 8 vertex, 0 to 7. Okay. So first you keep those entries. So these are the array index. These are the array index. Okay. The array will have how many locations in the sense? The array will have this many locations. n plus 2e plus 1 location. Okay, the array will have n plus 2e plus 1 location. What is n? N is the number of nodes. Okay, that is what 8. 8. 2e is number of edges. Number of edges here how many? 1, 2, 3, 4, 5, 6, 7. So 2e is 14. Okay, so 7 into 2 is 14. So 8 plus 14 plus 1. Okay, what is that? 14 plus 1 is 15. 15 plus 8 is 23. So this array will have 23 locations. This array will have 23 locations. Okay, how 23 location means? It is based on this formula. So when you represent using an array representation, otherwise it's called as compact representation. In that case, the array should have this many locations, n plus 2e plus 1 location, where n is the number of vertex, e is the number of edges, and plus 1. Okay, that many locations it should have. So this to represent this particular graph using an array, we need 23 locations. That is from 0 to 22. Okay, so these are nothing but the array locations, starting from 0 to 22 locations. Okay, fine. Now how this from this how we going to connect the edges? That is the question. That is the crucial question. Okay, fine. So what we are going to do is, see this graph contains how many edges? 7 edges. Sorry, 7 vertex. This graph contains how many vertex? 7 vertex. So these are the 7 vertex, right? These are the 7 vertex. Okay. So how to fill up these values? This is what we are going to discuss. These vertex should be filled with in each location of this array. Some value should be filled. 0th location represents 0th vertex. First location represents first vertex. Second location represents second vertex. So on and so forth. 7th location represents 7th vertex. But here we should fill up some values. How these values we are going to fill? That is the that is what our crucial question is. Okay, fine. Let us come to that. Fine. Okay. Now what we are going to do is, first we will fill up which location in the sense. First we will fill up 8th location. Why 8th location? You may ask. That is this graph contains how many vertex? 8 vertex. That is from 0 to 7. So 0 to 7 represents, each represents one vertex. Okay. So after the last vertex, so last vertex is 7. After the last vertex, what we have? 8. So that should be filled with n plus 2e plus 1. Okay. That should be filled with what? N plus 2e plus 1. What is n plus 2e plus 1? Already we discussed, that is 23. So that will be filled with 23. Actually, we don't have any 23 location. So that is the end of the array. Okay. Or you can say end. There is no such location. That is beyond end. The end is 22. It is beyond that. That 23 will come here. Right? Fine. Okay. Now this take vertex 0. Vertex 0 contains how many edges? You see, vertex 0 contains how many edges? It contains an edge, 2 edges. It contains one edge to 1 and it contains another edge to 2. Okay. So now in the 9th location you specify that 2 vertex. It can be any order. Vertex 0 is having an edge to 1 and also it is having an edge to 2. So that node number here we will specify. Vertex 0, it is having one edge to 0. Sorry, one edge to 1 and another edge to 2. So first we will enter 1, then you can enter 2. Otherwise you can enter in the reverse way also, 2 and 1. That is, it is having a edge to 2 and it is having an edge to 1. Right? Okay. After doing this, you so the edge detail of vertex 0 is available in which location of the array? 9th location of the array. That value you put here. That 9 will come here. Are you getting? The edge detail of vertex 0 is available in which, starting from which location? Starting from 9th location. Okay, starting from 9th location to how many locations? That how it will know in the sense. It contains 2 locations. Okay. So starting from 9th location to 2 locations. So 9 plus 2 is what? 11. So 11 will come in the next location. Okay, so for vertex 1 we will put 11. We will put 11. Why? Because vertex 0's edge detail is available from ninth location to 10th location. So next value is what? 11. That will come here. That will come here. Okay, fine. So in the 11th location you have to specify the vertex detail, edge details of vertex 1. So vertex 1, if you see, it has how many edges? Vertex 1, it has how many edges? It has again two edges. It has a edge to 0 and it has an edge to 3. Okay, so you can specify either 0, 3 or 3, 0. So 0 and 3, right? So again, vertex, the edge detail of vertex 0 is starting at 11 and it is going for how many locations? 2 locations. So add 11 plus 2 is 13. That will go into vertex 2. Okay. Now vertex 2 is having how many edges? 2 edges. What are they? 1, 2, 3 and 1, 2, 0. Okay. So from 13 again you can write either 0, 3 or 3, 0. So in the next location you put 0, next location you put 3. Okay, right. So now vertex 2, it contains how many, its edge detail is available in 13th location and it is having how many edge? 2 edges. So it is occupying, starting from 13, it is occupying 2 locations. So 13 plus 2 is 15. So the details of vertex 2, 3 will be available in 15. Okay. Okay. So now you go to vertex 3. It contains how many edges? Vertex 3, it contains how many edges? 2 edges. What are they? 1 to vertex 1 and 1 edge to vertex 2. So that we will enter here, 1 and 2. So that is in the 15th location we will say that there is a vertex, there is an edge to 1. Okay, from 3. Okay, because 3 is connected with 15, right? And also it has a vertex edge to vertex 2. Okay, so the edge detail of vertex 3 is available starting from 15th location and up to how many locations it is occupying? Starting from 15th location it is occupying 2 locations. Okay, so the next the edge detail of the next vertex should come at which location? 17. So next is which edge? 4. Edge 4. Edge 4 contains vertex 4. Vertex 4 contains how many edge? Vertex 4 has only one edge. It is having an edge to 5. That's all. So the edge detail of vertex 4 is available at 17th location. From 17th location, it is occupying only one location. Okay. So and it is having an edge to vertex 5. That is the meaning. Okay. So next edge details. I mean the edge detail of vertex 5 will start at which location? 18th location. Okay. If you see vertex 5, it has how many edges? 2 edges. 1 to 4 and 1 to 6. Okay. So starting from 18, it will occupy 2 locations, 4 and 6. Okay. So the edge detail of vertex 5, it is available from which location? 18. And it occupies how many locations? 2. That is 18 and 19. So the edge detail of vertex 6 should start at which location? 20. Okay. So vertex 6, it contains how many edges? 2 edges. What are they? 1 edge to 5 and 1 edge to 7. And it starts at which location? 20. So there is a edge to 5 from 6 and there is a edge to 7 from 6. Okay. So the edge detail of vertex 6 is available from 20 to 2 locations, 20 and 21. So the edge detail of vertex 7 will be available in which location? 27. 27. Okay. Sorry, 22, right? And edge 7 vertex 7 contains how many edge? Only one edge, that is to 6. Okay, so that will be kept here. It has only this vertex, this last vertex contains how many edge? How do we know that? It is having, in our case, the last vertex in our case it is having only one edge. Okay, so that here we are writing 23. So that here we are writing 23. Okay, right? For example, if it is having another edge, then this may not be 23. Repeating. Okay. For example, if there is an edge from say 7 to 5 also, If there is a edge from 7 to 5 also, then this will be 5. Okay, right? Okay, so this is how we represent using what you call compact representation. Okay, so so this is called as either compact representation or what you call as array representation. Okay, right, fine. So this is called this is the this comes under adjacency list, both linked list style and array representation. The next thing what we are going to discuss is adjacency multi-sets, multi-list, adjacency multi-list. Okay. So before going through this content, let us discuss this with an example first. Okay. See, let us take this graph, right? So this graph contains how many edges? First, let us identify that edge. Say, let us, these edges are numbered like this. This graph contains 6 edges. What are they? N1, N2, N3, N4, N5 and N6. Okay, normally we say E1, E2, E3, but here we are calling it as N1, N2, N3, N4, N5 and N6. Okay, right? So let us follow that nomenclature. So this is N1. Which edge? 0 to 1 is N1. Okay, 0 to 2 is N2. Okay, 0 to 3 is N3. Okay, 1 to 2 is N4. 1 to 2 is N4. This is N4. Okay, 1 to 3 is N5. 1 to 3 is N5. Right? And 2 to 3 is N6. These are the 6 edges. Okay, these are the 6 edges. Right? Fine. Now, okay, now this first, here the first location it says just whether this particular where edge is visited or not, something like that. Okay, so we are not bothered about this. We leave this blank. Okay, the next two location represents the edge, what edge it is. So N1 is 0 to 1, N2 is 0 to 2, N3 is 0 to 3, N4 is the edge between vertex 1 and 2, N5 is the edge between vertex 1 and 3, N6 is the edge between vertex 2 and 3. Okay, right. Now the question is how we are getting these values. So this how we are identifying means let's strike out this. Let us identify these things. Okay, we will do by ourselves so that we will get the clarity. Right. Now what should these things should be filled up? So here what we have 0, 1. So first you take this 0. Take this 0. Below you see where the first 0 occurs. It can occur either way. But leave this N1. Starting from N2 you see where the first 0 occurs. You can check here and here both the ways. So the first 0 is appearing here. Okay. So this location will fill up N2. Right. Now you take 1. Where again starting from N2 you see where the first one is appearing. Here there is no 1. Here there is no 1. Here there is a 1. Okay. So 1 is in which edge? N4. So put N4 here. Here we get N4. Okay. Right. Next come to the next edge. How we get this N3? Again this is what 0. Start from this 0. Go down. Where is the first 0 we identify? Here is the 0. So N3. So here N3 will come. Right. Then take 2. Go down and identify where the first 2 occurs. Here is the first 2 occurring. So this is in edge N4. So this becomes N4. Okay. Now come here. Okay. So this is 0. Go down and check is there where the first 0 occurs. There is no 0 here. There is no 0 here. There is no 0 here. There is no 0. So just keep this pointer as null. Nothing. It is not pointing anywhere. All these are pointers. Okay. Now take this 3. Where the first 3 occurs. No 3 here. Here there is a 3. Okay. So N5. So this becomes the second pointer becomes N5. Right. Now come to the next edge N4. There is a 1 here. Go down and check where the first one occurs. So here there is the first one. So N5. So fill this with N5. Right. Next. Take the next value 2. Again go down and check where the first 2 occurs. So here is 2. So that is in N6. So this will become N6. Okay. Next. So this is done. Now go here and check. So go down and see where the first one occurs. Is there any one? No. No. So fill up with null. Then the next is 3. Go down and check where the first 3 occurs. Here is 3. So 3 is available in N6. So fill this with N6. Right? Now we have reached the last edge. So 2. Go down and check is there any 2. There is nothing to go down. So fill up with null. Okay. Again 3. Go down and check is there any 3 occurs. There is nothing. So fill this with null. Okay. So this is how we got these edge numbers here. Right? Fine. Okay. Now how this so this is also one way of representation. So how it is representing this entire graph, that is the question. Okay, other than that we maintain a pointer. Okay, apart from this, so this is how first we create these edges. We create these edges and we fill up like this. Okay, right. Now in this edge there is another important thing. There are two pointers we are maintaining. Okay, so see here, this is an undirected graph. So there is an edge from 0 to 1 means it also means that there is an edge from 1 to 0. Right? There is a edge from 0 to 2 means it also means that there is a edge from 2 to 0. There is a edge from 1 to 3 means it also means that there is a edge from 3 to 1. Okay. So when you say 0 to 1, you have to refer this pointer. These two are pointers. Okay. But when you say 1 to 0, you have to refer this pointer. Okay. So that here it is mentioned 1 to 0. Similarly, when you say 0 to 2, you have to refer this pointer n3. When you say 2 to 0, you have to refer this pointer n4. Okay, that we will see how it works. When you say 0 to 3, you have to refer this pointer, which is null. When you say 3 to 0, you have to refer this pointer. Okay. When you say 1 to 2, you have to refer this pointer. When you say 2 to 1, you have to refer this pointer. Okay. When you say 1 to 3, it is here, it is null. When you say 3 to 1, you have to refer this pointer. Okay. When you say 2 to 3, it's null. 3 to 2 is also null. Okay. Let's see how this thing works, right? So now you have to first create an array of pointers. So we have an array of pointers. The size of the array will be equal to the number of nodes. Here we have how many nodes? 4 nodes. Here we have 4 nodes. Okay. So this will have. So here we have 4 nodes. Okay. So there are 4 pointers, right? Now the point of adjacency multiset is more than one pointer may point to the same link. Okay, right? More than one pointer of this set may point to the same list. Okay, all these are one list if you see, but more than one pointer can point to the same list. So for example, this is so this pointer corresponds to which vertex? Vertex 0. This pointer corresponds to vertex 0. This pointer corresponds to vertex 1. This pointer corresponds to vertex 2. This pointer corresponds to vertex 3. Okay? Right. So now when you say this pointer is pointing to n1, this pointer is pointing to n1, which means it is talking about this edge 0 to 1. 0 to 1. One edge completed. One edge completed. Okay? But it has how many other edges? 0 to 1 is done, but it has 0 to 2 and 0 to 3 also. How are you going to go through that? So this is corresponding to which vertex? 0. Okay. So already you have done with 0 to 1. So now you have to take which pointer? n2 or n4? We are talking about 0 to 1, not 1 to 0. When you come from 1 to 0, you have to take n4. Now you are coming from 0. Now source is what? You see. Where is the source? Source is which vertex? 0. So we done with 0 to 1. So you have to take n2 because this is the pointer corresponding to 0 to 1. When the source is 0, you have to follow through this pointer. When the source is 1, you have to follow this pointer. Now the source is 0. So follow this pointer n2. Okay, n2 is what? 0 to 2. So second pointer, second edge we have done. Okay, now also you see what is the source? 0. So 0 to 2 means you have to take this one. What is that? n3. What is n3? n3 is 0 to 3. So this is the third edge. Third edge. Okay. Again it is source is what? 0 to 3. So take this edge. So take this pointer. What is this pointer? Null. So stop. So now for this vertex we have identified all the 3 edges. Right? Like that we can identify for other edge, other vertex. Now take 1. Now the source is 1. Be careful. So 1 is pointing to n1. 1 is also pointing to n1. Okay. So now source is what? 1. It is 1. So it is, you should not take this as 0 to 1, you have to take it 1 to 0. If it is 1 to 0, you have to follow which pointer? N4 you have to follow. Because now the source is what? 1. So we have done with 1 to 0. So you follow the pointer corresponding to 1 to 0, that is N4. Okay? Right? In N4, okay, come to N4. Okay? So in N4, what you have? Where is where is N4? N4 is here. This is N4, right? So in N4, what you have? 1 to 2. In N4, you have 1 to 2. Now you see the direction is changing. Now what is the source? This is the source. 1 to 2. If it is 1 to 2, you have to take this pointer. Only 2 to 1, you have to take this pointer. Okay? So it is your source is 1. Your source is 1. So it is 1 to 2. So take N5. So here we have done with what? Here we have done with 1 to 0. Here we have done with 1 to 2. Now 1 to 3 is pending. So we have to follow which pointer? N5. N5 is what? 1 to 3. Okay. So 1 to 3 is done. But again our source is what? 1. 1 to 3. So you have to take this pointer. This is null. So stop. So now all the edges corresponding to vertex 1 is also done. Right? Okay. Similarly, we will see for vertex 2. Vertex 2. Okay, vertex 2 to N2. Okay, here. Okay, so it is what? 0 to 2. But our source is what? 2. So you should see in what way? You should not see as 0 to 2, you have to see as 2 to 0. If it is 2 to 0, you have to take which path? N4. Okay, so now we have done with one edge 2 to 0. Okay, now then we are going to N4. What is N4? N4, it is 1 and 2, but our source is what? 2. So you have to go from what? 2 to 1, not 1 to 2. 2 to 1. Okay. So 2 to 1, this edge is done. So if it is 2 to 1, then you have to follow which pointer? N6. Okay. What is N6? N6 is this. What is here? What is here? 2 to 3. Okay. Now it is 2 to 3. It is not 3 to 2 because our source is 2. So 2 to 3. Okay. 2 to 3 is done. After, if it is 2 to 3, then which pointer you have to follow? With this point, but this pointer says null, so stop. So this is how we identify all the edges for vertex 2. Okay. Now for vertex 3, coming to vertex 3, it is pointing to N3. So it is here what you have 0 to 3, but what is our source? 3. So we should take it as what form? 3 to 0. Take it as 3 to 0. So 3 to 0 we have done. 3 to 0 we have identified this edge. Next we have to follow which pointer? If it is 0 to 3, you have to follow this. 3 to 0, you have to follow this. So that says go to N5. So this is N5. Okay. In N5 you have 1 and 3. But our source is what? 3. So you have to take this way. 3 to 1. Okay. So 3 to 1 edge is done. So if it is 3 to 1, you have to follow this pointer, which is N6. Which is N6. So in N6, if you say you have 2 and 3 is there, our source is 3. So you have to follow 3 to 2. So this edge is done. Okay. So after 3 to 2, which pointer you have to follow? This one, which is null. So stop. Right. So this is how things are represented using adjacency multisets. Okay. Now we will see the definition of adjacency multiset. An edge in an undirected graph is represented by two nodes. Is represented by two nodes in an adjacency list. Okay. So there are two nodes. Okay. See, an edge is represented using two nodes. 0 is a node and 1 is a node. So there is one edge. Okay. So this will take care of not only 0 to 1, it will also take care of 1 to 0. Similarly, this is one node, this is another node. It takes of 0 to 2 and 2 to 0. This will take care of 0 to 3 and 3 to 0. This will take care of 1 to 2 and also 2 to 1. This will take care of 1 to 3 and 3 to 1. This will take care of 2 to 3 and also 3 to 2. Okay. Fine. So in adjacency multisets, in which nodes may be shared among several lists. Okay. An edge is shared by different paths. Okay. Here we have seen no? This edge is shared by different paths. It is shared from this path and also it is shared from this path. But finally, it will identify the particular edges for all the nodes. Right. Okay. So these are the different ways of representing graphs. So at the top level, you have three types of representation. One is adjacency matrix, next is adjacency list, and the third is adjacency multisets. See, commonly used thing is adjacency matrix. Okay, anywhere you go, mainly even though it has a complexity of order of n squared, mostly people follow this adjacency matrix type. Okay, maybe for programming convenience we can follow this adjacency list. Okay, right? So these two are the very crucial things. Okay, right? Let us stop here. Thank you.